we're looking today at something called Gibbs free energy. And Gibbs free energy is something that allows us to work out whether or not a reaction is feasible, whether a reaction can take place at a given temperature. So the equation that we need to know is this one. Delta G equals delta H minus T delta S. So what Gibbs free energy is doing is looking at the enthalpy change for a reaction and the entropy change for a reaction at a given temperature and working out whether or not that reaction can actually take place. We say whether it's a feasible reaction. So let's just think about what each of these are. So this is called the Gibbs free energy. It will often be referred to simply as free energy. We know that delta H is the enthalpy change, T is the temperature, and delta S is the entropy change. Now there's a few things we need to be aware of in terms of the units here. Gibbs free energy is frequently needed to be quoted in kilojoules per mole. Enthalpy changes will almost always be given to us in kilojoules per mole, but entropy changes, because they're small numbers, are often in joules per Kelvin per mole. So when we do our calculations, we're going to have to be aware that we're probably going to have to convert this. We could convert the enthalpy change, but then we'd have a Gibbs free energy in joules per mole. So often this is one that we have to convert. Also, if we have a think about the temperature, temperature is in Kelvin. So we can convert temperature into Kelvin, so degrees Celsius into Kelvin, by adding 273. So the easiest thing for us to do with this is to simply work through an example. So here's my example. I'll leave that there for a moment just for you to have a look at it. So let's work out the stages that we're going to need to go through. So here's our chemical reaction. We're given some enthalpy change of formation data and some entropy data. S there is our entropy data. I notice again that this is in kilojoules per mole and this is given to us in joules per Kelvin per mole. So we're going to have to do some conversions later. And also we want to calculate the free energy change for this reaction at 50 degrees Celsius. Step 1 is going to be for us to calculate the enthalpy change of reaction from our enthalpy change of formation data. So delta H is equal to the sum of the enthalpy change of formation of the products minus the sum of the enthalpy change of formation of the reactants. So let's look back at our information. The product are 2 molecules of sulfur trioxide. The reactants are 2 moles of sulfur dioxide and 1 mole of oxygen. So let's do this calculation. So delta H is going to be equal to 2 times the enthalpy change of formation of sulfur trioxide, because that was our product. So 2 times minus 395. And then we're taking away from that our reactants. So our reactants were 2 sulfur dioxides and 1 oxygen. So that will be minus 2 times minus 297. Now you'll notice that the enthalpy change of formation of oxygen is 0, and that is because by definition you can't form an element from itself. So the enthalpy change of formation of any element in its standard state is 0. So that's why that's a 0 there, and I haven't included that in the enthalpy change calculation. So that gives us an enthalpy change of the reaction of minus 196 kilojoules per mole. So step 1 has been done. We then want to do our entropy change calculation. So delta S, S is the symbol for entropy, equals the sum of the entropies of the products minus the sum of the entropies of the reactants. So let's do this calculation now. So our products again were sulfur trioxide. So there's 2 moles of sulfur trioxide. So that's 2 times 256. And we're taking away from that the entropies of 1 molecule of 1 mole of oxygen and 2 moles of sulfur dioxide. So let's do that part. 205 is the 1 mole of oxygen, and I'll put these all in a bracket. 2 times 248. So this is the entropy of my products, and these are the entropies of the reactants. That calculation gives us minus 189 joules per Kelvin per mole. So we've calculated the enthalpy change and we've calculated the entropy change. I said earlier that we're going to have to convert one of these so that they are in the same base unit of joules. So I'm going to choose to divide this one by 1000. So here I'm going to convert into kilojoules per Kelvin per mole. So that will be minus 189 divided by 1000 gives me 0.189, minus 0.189 kilojoules per Kelvin per mole. Right, so the question asked us to calculate the free energy change, or the Gibbs free energy change for the reaction at 50 degrees Celsius. So let's just write the equation we need again. Delta G equals delta H minus T delta S. The energy change is equal to the enthalpy change minus the temperature multiplied by the entropy change. I'm also going to have to convert temperature into kelvins. So I'm going to convert 50 degrees Celsius into Kelvin. So as we looked at earlier, 50 degrees Celsius plus 273 gives us 323 Kelvin for the temperature. So now I'm in a position to be able to put everything into my equation. I'm just going to circle all the information. Delta H we've calculated here. Delta S we've calculated here, but we converted it at this point, and temperature we've converted into Kelvin here. So let's put those pieces of information into my Gibbs free energy calculation. Delta G equals minus 196, which is the enthalpy change, minus, and I'll put this in brackets, 323 multiplied by minus 0.189. And that gives me, at the end of it, minus 134 kilojoules per mole. So what's the significance of this? Well, this is a negative value. Any value for a Gibbs free energy change of less than 0 means that a reaction is feasible. I'm going to deal with that more in future sessions. All I really want us to do today is actually just be able to calculate the Gibbs free energy, but I'm just going to write here that this reaction is feasible because delta G is less than 0. That doesn't necessarily mean that the reaction is going to happen spontaneously, and spontaneously means just occurs without any outside influence. The reason being is the activation energy for this reaction is very, very high, and this particular reaction, whilst it can theoretically occur, it is feasible, it doesn't occur without a catalyst. So there's the calculation. I'm going to zoom out to the whole page, or whole calculation there, just in case you want to pause the video and have a look at it. And then we're just going to think about a few summary ideas. So in terms of the key points we need to take away from here, I would suggest that What the most important thing in terms of conversions is delta S will need to be converted into from joules per Kelvin per mole to kilojoules per Kelvin per mole. So in order to do that, we'll need to divide that by 1000 to get to kilojoules per Kelvin per mole. We also need to be able to convert temperature from degrees Celsius to Kelvin, so we add 273, and then there's three equations we need. We need delta G equals delta H minus T delta S, and that's something you have to learn, and you have to know that equation, the free energy equation, and also that delta H equals the sum of the enthalpy change of formation of the product minus the sum of the enthalpy change of formation of the reactants, and delta S is equal to the sum of the entropies of the product minus the sum of the entropies of the reactants. Thank you very much.